Good. So let me put a start time. So it is 10:20. Okay. And then share screen. Go to my phone here. That start connecting. And while that's connecting, let's me look up this number. So here's the homework for your class. Hey, how come it says problem with loading? Maybe if I refresh it. Good. That looks better. Oh, let me get my camera going. Okay, so that loaded better. Let's come down to chapter 39 and number 38. Okay. So it says what? In a typical color TV picture tube. This is getting to be an old question. I don't know if we have too many picture tubes anymore with all our LCD screens. And even right before that, the plasmas and the, what are those, DDL? DLL? Yeah, digital light. DDL or DLL? Was digital light. Huh. Anyways, but I don't know if you're familiar even with the old computer screens, where they're 18 inches or 24 inches long, but they shoot electrons from the back. So maybe here's the screen and the picture tube looks like this, and they've got electrons and they shoot them and then they control them and they hit the screen at different locations, giving off light, and that's how you get an image formed on the screen. And so you have to get them moving really quick, and so you accelerate them, and that's what this problem is about. A typical color television picture tube, the electrons are accelerated from rest through a potential difference of 25,000 volts. Now, this question's a little unfair to those of you who haven't gone through 122 because the work done, which results in the kinetic energy, so that everybody does know from Physics 121, but it is the charge of the electron times the potential difference. And so this is what we referred to as electric potential energy. So really more for people who are listening later on to this recording, half of you are going to go, oh, I don't recall the electric potential energy. And so that's a chapter 25, that's a Physics 122. So know this much, that I wouldn't put something like this on the exam, although the author puts it here because in his mind, people went straight through the book and they've already done chapter 25 here. And I even debated if I should put this as a homework one, but thought that this first step here wasn't too much of a hindrance, even for those who haven't had it. So what I'm saying is don't stress about that one if you don't already know. So the first part of this is related to that equation here. It says, what speed do the electrons have when they strike the screen, and what is their kinetic energy in joules? So maybe I'll do B first, because that's what I've set out to be. The kinetic energy is the charge from the voltage. So if we take the charge of the electron times the voltage, we have it. And again, for those of you who haven't gone through 122, you need to probably look up somewhere what is the electrical charge of the electron. And for those of you who've gone through 122, I keep telling you to, hey, memorize that. Hopefully you still remember, but it's 1.602 times 10 to the 19 coulombs. And then in this case, the voltage is the 25,000 volts. And again, unless you've gone through 122, a volt is a unit that says how much energy you get per charge. So this doesn't mean we'll get 25,000 volts because we don't have a full 1 coulomb of charge. In fact, we got a very small amount of charge. So we're going to end up getting a small amount of kinetic energy. Although it's a small amount of kinetic energy, as you'll see when we do part A here, it goes really, really fast. And that's because the electrons are so light, so little mass. And so to have even just a small amount of kinetic energy means they probably are going very, very fast. All right, so it's part B here, or I'll call it the first step, that is, like I said, a little unfair to any of you who haven't gone through 122. So let me just calculate this out. This would be their kinetic energy, 1.602 times 10 to the negative 19 times 25,000. And so this is saying that we've got 4.00 times 10 to the minus 15 joules. So that's I guess the first step, even though they've asked it second. Now, for the rest of you, part A is really the relativity part of this. And the reason I grabbed this one is because I did want to make sure that in your mind, you don't do something like this. You don't say kinetic energy is 1/2 mv squared. The big part of this lesson was that kinetic energies, have a new formula, what I would call a more complete formula. Just like momentum is no longer just mv. Just like the time as seen by one observer is not the same as the time seen by another observer. So we've got some new formulas. Maybe I'll just put momentum here first, even though it's not related to this problem, but it's this extra gamma factor. And so time is dilated by an extra gamma factor. Length is contracted by an extra gamma factor. And so really we would say that Newtonian physics discovered really the physics of what happens when gamma is small, as small as it can get, which is about 1. And so if you just set that equal to 1, you get your common mv that you were exposed to back in physics 121. But the better formula for kinetic energy is gamma minus 1 times mc squared. And that one's a little harder to see, that at low speeds, it's the same as 1/2 mv squared. I think I did that in the video lecture, so let me not try to do a Taylor expansion and show you that. But what I do want to get out of this problem is that when you go to calculate the kinetic energy, this is what you would think in your mind. Gamma minus 1 mc squared, a more accurate equation. Not to say you should forget the 1/2 mv squared. The 1/2 mv squared is a great one to keep in mind. You just want to make sure that if you ever see anything going more than 10% the speed of light, that this one is just going to be so far off, you got to go to the more accurate one. So still use 1/2 mv squared for things that go under 1/10 the speed of light, which is really so many things in the world we live in that this is really probably the formula and the thinking you'll do most of the time. But for this problem, it's hard to tell if this is enough to get it 10% the speed of light or greater. But I would say, since I don't really know, and more importantly, because it's in this chapter, I should probably do this more accurate equation here. All right, so that's what I'm going to do here. So I'm going to put here this kinetic energy, which is the 4.00 times 10 to the negative 15 joules. And I'm going to put this gamma, which has to do with the speed. So that's where the speed's going to come in. And then I can put in this mass. And so that's another one that you might need to look up. 9.11 times 10 to the negative 31 kilograms is the mass of these electrons. The speed of light, hopefully that one you've got memorized by now. 3 times 10 to the 8th meters per second, and square it. So this would give me a gamma minus 1 of, and I'll just grab my calculator, especially since the energy is already there. So I'll divide it by the 9.11 times 10 to the negative 31. And I'll also divide it by 3 times 10 to the 8th squared. And I thought it would be a bigger number than that. If I did my calculation right, I'll check the answer here. 0.0, I'll call it 49 is gamma minus 1. And that means then gamma is 1.049. Okay, so my calculator, I'm going to add 1. So there's my gamma factor. Now, I always like to jump right to gamma squared because gamma has a square root in it, and I'd rather deal with gamma squared than just gamma. So let me hit a square on here and say gamma squared is about 1.1. And the reason I like that is because gamma squared is 1 over 1 minus v squared over c squared. So on to a next page, I can cross multiply this equation here. And so I'd get 1.1 minus 1.1 v squared over c squared. And that equals to 1. And so I would get 1.1 v squared over c squared, move the 1 over to there. So that's a 0.1. And then grabbing my calculator, I'll go 0.1 and divide it by 1.1. And then take the square roots of all of that. And so V over C is 0.302, or finally, velocity is about 30% the speed of light, which makes me feel good that I didn't use the 1/2 mv squared, because remember, this would only be useful if I was 10% or under, and this one tells me the more accurate one and tells me I'm at 30%. So would have gotten a very wrong number had I used 1/2 mv squared. It wouldn't have been a good approximation there. And since I was kind of questioning that low speed, but now that I think about it, that seems about right, because 500,000 volts would be gamma equal to 2, because that's the rest energy of an electron. So, yeah, now I feel more comfortable with that. But I'm going to look at this one anyway. So let me scroll to the
I think you are correct.
Solutions here. Good. So there's B and there's C. Thank you. Yep. So lucky me, I got it right.
All right. Thank you.
Nice. Okay, you bet. All right. Well, I'll flip back over here. See if you guys wrote anything in the chat or just kind of. So, well, this is a good sign that I don't have an overwhelming number of questions. That's good. I was able to do a couple of solutions and get you guys' test graded. That was good.
Yeah. Oh, the last homework,
Uh-huh.
I had it all. Yeah, I had it all done, and I got caught up on another test, so I turned it in a day and a half late, I think.
Yeah, no worries. I think you sent me an email too, right?
I put it as a
on
the assignment.
Yeah. And when you do that, then Canvas sends me an email. So yeah, I saw it. And no worries. No
Okay.
penalty or anything like that.
Thank you.
Yeah.
All right. Well, I've got to go get. I got to go do some math homework. I'll see you on Friday.
All
Most
right.
likely.
I think I'll pause the recording until somebody comes back in. Hey, okay, let's try this one here. This was an email question sent to me here. This will be good here because this is the 121 class, and this is the cans in a box. And here's the picture. And this one illustrates, again, a couple of techniques that tried to get across in the other videos I made earlier this week. And let's see if I can kind of draw a decent picture here. That's not a very good circle, but I'll take it for what it's worth. And there's two cans in a box, and they don't fit side by side with each other. And the problem says this. It says, Jamie puts two filled aluminum cans with a total mass, and so let me go mass total, equaling 0.364 kilograms. And a radius of, let me put that above, so I would assume they each have this radius of 3.12 centimeters in a cooler. Okay. The width of the cooler is 10.2 centimeters. So you can see one can's diameter would be a little over 6. So two of them would be, well, about close to 12 and a half. And so it doesn't quite fit side by side here. Okay. In fact, there it says not quite wide enough for two cans. So they stack. The normal force on each wall pushes inwards at the cans. And so they say N inward, ignore friction. Hint, the torque equation and geometry are easiest using the origin at the center of the lower ball. And that's a great hint. But it's something I want to talk about. In fact, there's two things I want to talk about, and it really comes back down to this, that they gave us the mass of both cans. Let me just divide that in half. So 364 divided by 2 is 18.2. No, guess I didn't need a calculator for that, but I get lazy. All right, so there's the mass of each of them. See, because one of the first questions to ask, and the second one is also where the hint is given, but the first one is, do you want to look at this as individual cans? So we would do a free body diagram of can number 1 and maybe then a free body diagram of can number 2. Or do we want to look at it collectively at one object? So what I hope you got out of these last few lectures here is sometimes there's an advantage to one versus another. And this was that important distinction between interior or internal forces and external forces. See, internal forces, because of Newton's third law, there'll always be an equal and opposite. So if you add up all the forces, and when you say that, you say I'll do all the forces, not just the external, but also the internal. Since the internal ones would be coming from internally, they would have inside of your system the equal and opposite. And so all internal forces would add up to 0. The reason that's important then is we could then say, look, you don't have to worry about internal forces. They will always come out to be 0. It doesn't matter if they're big or small. It doesn't matter if they come from gravity or contact or a string or a rope. It doesn't matter if they come from a magnet. None of that matters. They will always be equal and opposite. And so you can ignore them. And so if you have some kind of force that's kind of complicated, then it might be good to ignore it. And looking at these cans where they touch, there would clearly be forces between these two. Now, they obviously clearly touch here, at least I'll call this the bottom one touches. So your author calls this the normal force on the wall. This one touches also, so there is a push this way. Well, maybe I should put it back here, push this way, normal force. It's touching the bottom here, so there would be some kind of normal force here, which your author calls the normal force from the floor. And here's what I'm getting at in this first step. The first time I would sit down to do this, I would say, okay, what are all the forces? Because I got to draw the free body diagram. Now, of course, there is the gravitational force of this lower one, which would be at its center of mass. And there would be the gravitational force of the upper one, which again would be at its center of mass. And then there would be this contact. And this is the one I really want to focus on. Because if I were to think about a free body diagram that was only the lower can, then I would have to include gravity and everything touching it, which would be this force, the floor, the wall, and the upper can. And then likewise, if I were to think about a free body diagram of just the upper can, I would have to say, okay, what are the forces on this upper can? And I would have to think about the force of gravity, okay, and everything touching it, which would be the wall, but it would also be the lower can. So the lower can puts a force on the upper can, and likewise, the upper can puts a force on the lower one. Now, the good thing is I know that they're equal and opposite. So if I do separate free body diagrams, once I figure it out for one, I also know it for the other. So that's probably the good news. But my point is that if I do a free body diagram with just one object, I've got to worry about this force between them. And then that's where hopefully the light bulb goes off. And you go, wait a minute. If I were to do the free body diagram, let me just write something down here, a note for a little bit later. Okay. But if I were to do a free body diagram, my first reaction, and I don't know if this is going to come out right. You never do on these problems. That's why you got to kind of struggle through them. But my first reaction is to say, let's do a free body diagram where the object I'm thinking of is the collective system of both cans. And as I was alluding to and trying to say, sometimes this could be better. And it's better because when you do that, you don't have to worry about the internal forces. This would kind of be a silly example, but if I were to just look at the can by itself, or here we go, worse yet, half the can, I would have to then be concerned about all the intermolecular forces between the left and the right of the can. But when I think about the whole can, I don't have to worry about those intermolecular forces. That was the neat thing, that when we were doing problems of just a single object, like a can or a baseball tossed across the room, we only worried about the force of gravity and said it made a parabola. We never worried about the intermolecular forces because they were all internal. And if you worried about them and added them up, you would get zero. And so you can ignore them. And early on, when we were doing projectile motion in chapter 4, we never justified it. So this is my chance of kind of going back and saying, this is how it worked. This is why it worked, because of Newton's third law. And so just like we don't have to worry about the intermolecular forces when we deal with the can, we only have to worry about the external one, like the force of gravity. I'm trying to say the same thing here. If you hook your two cans together. And even though there is an interaction contacting them, those are internal and you don't have to worry about it. And that is a force that looks to me like it's a hard one to get. I don't even want to label it. In fact, I'm looking at the author's picture, and the author shows not the force. And it looks like he's even reasoned out. Let's see, it would be, no, it needs to have a horizontal component. So so the author hasn't really drawn the whole force, but has drawn the vertical component of that. Looks like there would have to be a sideways one also. But let me not get too involved in trying to figure out what this force would be. Doesn't look like it'd be too hard, but that's what I'm trying to avoid. I'm trying to avoid having to think about that. I'm trying to avoid doing that. So that's a strategy. So I'll say it again, and maybe I'm again talking a little too much here, but just wanted to point out here that you should know this strategy, because this strategy of hooking things together can be useful, or taking things apart can be useful. Because again, if you don't know the force between the cans, you can see that if you put them together, you don't have to worry about it. It's internal. Now, with that said, if this problem said, what is the force between the two cans? And this problem is not asking that. It might be kind of fun to actually do it and extend this problem. But know this, that if you're trying to solve for the force between the two cans, you cannot do it with a free body diagram that puts the two together, because putting the two together, they become internal forces and they cancel each other off. So that's the good and the bad about putting the cans together. All right, so for this problem, I think my first gut feeling is, number one, put the cans together so that this force between them becomes internal. I don't have to worry about it. Yay. And maybe even give me the mass of the whole thing anyways. Okay. Now, with that in mind, now let me draw the external forces. So there would be an mg for can at the bottom and an mg for the can at the top. Again, my approach is to say it's the force of gravity and everything touching it. All right, so what's touching it? Well, down here at the bottom, and maybe just they don't overlap, I'll put a normal force from the floor. Also contacting it is a normal force from the wall over here on the bottom can, but also touching it is a normal force from the wall. And of course, one of the first questions to ask is, are those two the same? Your author has labeled them the same. And we'll think it through here in a second, but the answer is yes, they are the same. But for me, I'm going to call this maybe normal force from the wall, left and right. And that would be it. That's everything touching it. And again, thinking of it as one object, I don't need to worry about the upper can touching the lower can. I would only worry about that if my free body diagram was talking about the bottom can or just the upper can. All right, so the two conditions of equilibrium are the sum of the forces in the x direction have to be 0, and the sum of the torques have to be 0. And as I mentioned on some of the other videos, the keeping it simple and all the forces are in the XY plane, this statement is really two statements saying all the forces in the X direction and all the forces in the Y direction have to come out to be 0, which means then forces in the XY plane can only make things rotate on a Z axis. So we only have to worry about torques rotating around a Z axis. So our two conditions of equilibrium become, I'll say 3 equations, but now I really get to the second thing I want to say. So let me backtrack. The first big thing is internal and external forces and how do you pick your free body diagram. Do you pick them collectively together? And I would say yes in this case, because that makes the contact between these two internal, and you don't have to worry about internal forces. They always add to zero force and zero torque. Okay, so that's why I chose that. Now, the other thing I want to point out here is related to the hint, and it's also related to what I said in the other videos, if you got a chance to see those other videos, is that we write this as one equation, that the sum of the torques is equal to zero. But really, this is an infinite number of equations. This is not just one, because this is saying the torque about any axis. You see, if it was non-zero around any axis, then it would rotate. And the whole idea of our static equilibrium is to say it doesn't rotate. It doesn't rotate around any axis. So this, we could pick an axis, say the middle of the bottom can or the middle of the top can, or where they contact, or where the bottom can contacts the floor, or where the bottom can contacts the left wall, or where the top can connects the right wall, or for that matter, we could just do some random point over here. And so whatever point we want to use, some of the torques have to be zero. So my suggestion, and hopefully this is an obvious suggestion, and that's what the hint is to say, well, why don't you do the torques around the axis that makes the problem the simplest? Yeah. All right. And so the author gives you the hint. It says the torque equation and geometry are easily done using the origin, okay, of the lower. Now he says ball, but, and I guess these could be thought of with balls instead of cans, but either one would work. But I'm going to go with cans. So lower can. Now, I want to expand on that and say, well, why is that the best one? Because obviously when you guys start taking your quiz and your final exam, there might not be a hint there. And so you go like, okay, well, why is this the best one? So let's calculate this idea of torque. Torque can be thought of, and there's two nice equations, F R sine phi and R perpendicular F. Both of those are really saying the same thing. This one, if I can just kind of take a moment out of this problem and review, I like to kind of make a little bolt. It's supposed to be a bolt. And I like to put a wrench on it. Okay, so I got this wrench on the bolt. And over here, somebody grabs it and applies a force off in this direction. I think you will see that you can view this force, and I'll maybe change colors here, as its components. And so if you view this force as a piece made up towards the bolt itself, and another piece perpendicular to it, the part that is perpendicular is the part that makes it move. And so if this is the R, if this is the distance out, and then this is the perpendicular amount, well, we might say that the torque is RF perpendicular. But you see that if this is the angle phi that is between the R and the F, you would get the perpendicular amount by saying it's RF sine phi. So if you put that into here, this is where this equation comes from. And I suppose we could think of this as a third way. So you could think of the equation like this or like this. And these are really kind of the same thing. But it's also, this is the same thing too. This one's a little harder to see, but if you made a extended line out from F, and this is R, and then you made a big triangle where this line coming out is perpendicular to the line of F, if you just regrouped the R and the sine phi, you'd be looking at this triangle involving R's, not the triangle involving the F's. And R sine phi would be this perpendicular distance. So R and sine phi together give you that. I guess what I'm really saying is this is maybe the obvious equation for torque. And if you put the R and the sine phi together, you get the perpendicular distance of R. If you put F and sine phi together, you get the perpendicular amount of the force. And that's probably the easiest one to see. It's the amount of force that is perpendicular to the wrench that actually turns the wrench. But coming back now to this problem, then I would say that you can see that if R was 0, you would end up having forces, but yet no torque. And so that's how you can try to make these problems a little bit simpler by looking at any force that would give you either a 0R or a 0R perpendicular. And that's what this center of the bottom can does for us. That's why the center of the bottom can is probably the best place. So again, luckily, because this is a pretty hard problem, the author helps us out by giving us a hint, but I do want to explain the hints. All right. And so really, I hope I'm not going too far off this problem, but because this is a hard problem in of itself, but I did want to point out two important problem-solving strategies, that is grouping things together to get rid of internal forces and picking a good choice of the pivot. Both of those can make the problem a lot easier. So I think you already saw how putting the two together allowed me not to worry about the force in contact between the two cans. And now I hope you see the second big thing is by picking the pivot to be right here, the torque from the weight of the lower can, the torque from the floor, and the torque from the left wall all come out to be 0. Because if you extend a line through any of these, they will go right through your pivot point. So your perpendicular distance, R perpendicular, is 0 for this force and this force. And of course, technically just R, not even R perpendicular, but R is 0 for this one. So all of these contribute nothing. So that's why I'm going to go ahead and do this equation first. The sum of the torques in the Z direction have to be 0. And to make my life as simple as possible, and hopefully you to kind of catch on how to make these problems as simple as possible, pick a wise place for your pivot. And so I will pick this spot. So when I go to calculate the torque, there's really just a torque 1 and a torque 2. Even though, back to my free body diagram, I see 5 forces here. 1, 2, 3, 4, 5. And at first glance, then, you would say, well, I must have 5 torques. But what I'm trying to point out is that this wise choice of this is your pivot makes that torque, and that torque equal to 0. And so the only torques we get is the torque from the weight of the upper can and the torque from the right side wall. Okay, so let's do the torque from the weight of the upper can. So I'll go ahead and use this formula for torque, because if you look at R perpendicular, so I'm going to draw a line for the weight. This would be the perpendicular distance. Maybe you could see it best in the original picture, but it would be this distance here. And that's perpendicular distance right here would really be the whole distance minus a radius 1 and minus radius 2. So maybe I will write it as width minus 2r. But I'll put in the numbers. The width is 0.102 if I do it in meters. And the radius is 0.0312. So that right there is that perpendicular distance. Now, the amount of force is mg, although I need to be careful with my m, because remember earlier on, there would be the m of the whole mass, or there would be the m of the individual one. Okay. Or, now that I think of it, we could do the center of mass right here. Oh, that's not a bad thought. And that's what the picture is. I see. That's what his mg is. Earlier, I thought his mg was the mass of one can, but now I see this is the center of mass. Oh, I kind of like that. But I've kind of already committed to what I just said. So let me continue on and just say then that this would be the mass then of one can. And so this is the 0.82. And the G is the 9.8. Okay, and then plus. Okay, so just to make sure you understood, this is the torque from the force of gravity from that upper can. Yeah, now I think about it, I should have just put the two together in my free body diagram and put it right there. Yeah, I do like that better. But I'm going to stick to this one. All right. And then let me point out here that torque would be pulling it. So if you kind of think of this as the pivot, and the torque pulls it down this way and rotates it in a clockwise direction. Rotate it clockwise. That is a negative direction by tradition. So I'll stick to tradition and then call that a negative torque. So there is my negative torque. In fact, as long as I did that much, why don't I just get out my calculator and see what that comes out to be. So this is the 0.102 minus 2 times 0.0312. Okay, so that's the leverage arm times the mass of one can times 9.8. So this is a torque, and it's negative 0.0706. And if you watch your units here, this would be a Newton, and then that's the distance of meters, so it's a Newton meter. And I'll say it again, don't put that as a joule. It's going to sound like an energy and be confusing, and think of it as an energy. And so we never call torques joules for that reason. Otherwise, we get ourselves confused and confuse other people. So, and of course, energy is a force times the distance it moves. And so back here in this would be the energy, force times distance, and then torque is force times this distance. So again, it's just a way of keeping those separate. That torque and energy, which are both force and distances, but they're different distances, so they're different quantities, they're different ideas, and we don't want to mix them. So calling them joules could make us think we're going to mix them. So don't do that. Okay, so this is the negative torque. Then the positive torque is coming back here to this free body diagram, is this wall pushing this way. And so if I do R perpendicular, I would need this distance. Now that distance is going to be a little bit harder. We already said this distance down here, let me just put a little diagram here, is W minus 2R. And this distance we'd like to find, fortunately, the distances between their centers would be pretty easy. That would just be 2R. And so if you think of this as a right triangle, and maybe you call this extra distance y, you could come over here and do kind of a Pythagorean theorem and say, okay, so y squared plus width minus 2r squared is equal to 2r squared. And so if we multiply this out and simplify, we get a y squared plus, and so this would be a w squared. Let's see, a minus b squared. This would be a squared minus a 2, an a b, and then plus a b squared. And I'll write it that way because that's what I have on the other side of the equation, and that will cancel off. And so y squared, if I bring this to the other side, would be 4wr minus w squared. And so if I take the square roots of that, I would get just y by itself. And let me get a number to that. Okay. Because down here with this calculation of torque, I'm trying to say that the torque from this wall would be the y times the normal force from the wall on the right-hand side, and it would be pushing it in a clockwise direction, excuse me, a counterclockwise direction, and so it would be a positive torque. So that's why I'm trying to find this y so I can put it in here. All right, so grabbing my calculator, I've got 4 times, and the width we said was 0.102 times the radius, which is 0.0312, minus 0.102 squared. I'll just hit enter for a moment, and then take the square root of all of that. And so it looks like I'm getting a distance of 0.0482. There's my value of y. And so calculating it out makes it a little easier to put into here, 0.0482 meters. And then there's the normal force, and that would equal to 0. And now that will allow me to get the force from the wall. So if I move this over, it'd be 0.0706, be positive. And if I divide it by the 0.0482, I would get a force of 1.47 newtons. Yay! And so that's the normal force from the wall on the right. And I don't know if the problem really said left or right. It should have, because what I have here is the right. But if we wanted to extend this problem a little bit further, remember earlier on we said the two conditions of equilibrium are that the sum of the forces in the x, the sum of the forces in the y, and the sum of the torques around z all have to be 0. And we've only dealt with the torques in order to get this force from the wall. But if you look at the forces in the x direction, and you go back to these 5 forces, you can begin to see that the 3 of them are down. Well, 2 of them are down in mine and 1 is up, and then these are left and right. So if I take the sum of the forces in the x direction, there would be the normal force from the wall on the right. And I guess I should be careful. Let me just put this here, normal force for the left. I probably back here should have said this is the, when I put a positive here, this is the magnitude of it. So I've got the magnitude of it. Because the one here on the right is actually pushing left, and traditionally that's a negative force. So that's why I wanted to say that's the magnitude of it. And then I have the force from the wall on the left, and that has to equal to 0. So that tells me the force on the wall from the left has to be equal in magnitude, but opposite in direction. So it too is the same number and is a 1.47. And that's why I think your author here of this problem didn't specify which one to work with and labeled them the same. This is the justification of why they are the same. And in fact, if I even went on to say, let's do the sum of the forces in the y direction, I would see here that I have an mg in the downward direction from the lower can, another mg where the mass is the individual ones pushing down, and then I have the force normal from the floor, and that has to equal 0. So that would tell me the force from the floor is 2 mg, where again, the m is the mass of an individual can. So this is just the total mass of the collection of the 2 cans. Makes sense. The floor is pushing up equal to the weight. So the 2 together is 0.364 times 9.8. So this would be 0.364 times 9.8. And if the problem had asked, what is the force pushing up from the floor? I would say it's 3.57 newtons. Now, maybe since I've been talking for a while, I'll call this quits and we can move on to another question. So I was kind of curious, and I'll just kind of set you up. But, now that we've done all that work, this would have been a much harder problem had they asked for what is the force of contact between the two. And this will take me all the way back to the beginning. Remember that by grouping them together, we were able to avoid that. But if the question asked for it, we have to do a free body diagram that would only include one of the cans. It doesn't matter which can. Why don't I call this the top can? So if I look at the forces on the top can, there would be a force from the wall on the right. There would be the gravitational mg of just one can, and then there would be this contact. And I said I wouldn't go that far, but I got it now. You could now see that if you are going to be in equilibrium and you don't know anything about this, you could label it as an upward force and a horizontal force. And knowing that the sum of the forces in the x direction have to be 0, you would have Fx minus the force from the wall, which we said was 1.47. That has to be 0. And so the x component is 1.47. The upward forces, the sum of the forces in the y direction have to be 0. So that would be force in the y minus mg, where again, m is just one can. And so the force in the y direction would be mg, where the m is only one can. So it's the 0.182 times 9.8. point, which is, I guess, half of what I got before. So this would be a 1.78 newtons. And now to get the magnitude of the total force making contact with the upper can, and therefore also the lower can, I could do the Pythagorean's theorem by saying, okay, well, this is the x component and this is the y component, and I can combine them and get it. So this would be the 1.47 squared plus, I'll just go last answer squared, and then take the square root, and this would be 2.31 newtons. And so the force that the lower can puts on the upper can is then this number. So obviously we went way beyond what the question asked. And we also touched on some strategies that would help you solve them. Hopefully all that was helpful. All right, take care. In fact, maybe this would be a good time to call it quits here for our break. So I'll stop recording.